In this section, let's talk about all the out-of-memory error exceptions thrown for different memory spaces in the JVM. So what is out-of-memory error? This exception simply means that the JVM has run out of space in any of the memory pools and cannot proceed further with the process execution. It's an unchecked exception and it's subclassed from Java Lang virtual machine error. This picture shows the hierarchical structure of the out-of-memory error exception. Here are all the out-of-memory error exceptions that the JVM can report. The JVM can report these exceptions if the Java heap space is full, or the collective GCs have exceeded the GC overhead limit, or when a huge array is allocated by the application. We can also see the out-of-memory error exception for the permanent generation or meta space, the compressed class space or native memory. In the next slides, we'll look in detail at all of these out-of-memory error exceptions. Before we go into the details of the out-of-memory error for the Java heap, let's first see what resides in this memory pool. All the Java objects get allocated in the Java heap. This example shows that a new string object is being created. It gets allocated in the Java heap. First, it stays in the young generation part of the heap, and if it survives long enough, it gets moved or promoted to the old generation. This error means that the Java heap is completely filled with Java objects and the application is requesting to allocate more objects. This error also means that the JVM had already invoked full GC, but it couldn't free up any space. As we learned in the previous section, here the problem could be that the Java heap is sized smaller than the application footprint, or the application is unintentionally holding on to some set of objects in the Java heap. GC overhead limit exceeded. This message means that there have been too many GCs and those collections have not been able to claim much space. After a garbage collection, if a Java process is spending more than approximately 98% of its time doing garbage collection, and if it is recovering less than 2% of the Java heap, then this out-of-memory error exception is thrown. This exception is typically thrown because the amount of live data barely fits into the Java heap, and there's very little free space left for new allocations. The JVM could be going through these excessive GCs due to any of the memory pools becoming full. GCs might be happening because the Java heap is running out of memory, or the permgen or meta space does not have any room left. Requested array size exceeds VM limit. This message indicates that the application attempted to allocate an array which is larger than the maximum permitted array size or the configured Java heap size. For example, if an application attempts to allocate an array, let's say of 512 megabytes, but the maximum heap size is set at 256 megabytes, then an out-of-memory error exception with this message will be thrown. So for this error, the problem is either a configuration issue, that is, the heap is configured too small, or the application is attempting to allocate a huge array. Before looking at the out-of-memory error message for the permgen, let's first take a look at what's stored in the permgen. As we have learned in the previous lesson, classes and class metadata are stored in the permgen, which includes static and dynamically loaded classes. And to reiterate what I had already mentioned, permgen has been replaced with metaspace in JDK 8. This out-of-memory error means that the permgen space is full with the loaded classes and their metadata, and the application needs more room in the permgen to load more classes. When the permgen fills up, a full GC is invoked, and this message means that before throwing the exception, the JVM had invoked full GCs to collect garbage in the permgen, but those GCs could not free up any space. This error could be an indication that the permgen is sized smaller than the footprint of classes and their metadata. Or there is some sort of memory leak and the application might be unintentionally holding on to some classes or class loaders, and that might be preventing the unloading of classes. Since JDK 8, the metaspace holds classes and class metadata. As we learned last week, the metaspace is not part of the Java heap space and is allocated out of native memory. Out of memory error for the metaspace. Now the question that comes to our mind is, if the metaspace is unlimited and is allocated out of native memory, then why would we see this exception? The metaspace by default is unlimited, but we can limit it using the JVM option max metaspace size. A full GC is triggered to collect the dead classes and their class metadata when the metaspace usage reaches its capacity. So the out of memory error for the metaspace means that the metaspace is almost full and its usage is close to the specified value of max metaspace size, and the garbage collections are unable to reclaim any space in it. This error could be an indication that the metaspace is sized smaller than the application's requirement for its classes and class metadata, or it may be a symptom of classes or class loaders related memory leak. If the JVM is configured to use compressed class pointers, which means that the class pointers should be compressed, then a separate space called the compressed class space is maintained as part of the metaspace, which is used to store the class pointers. This error message means that the compressed class space is running out of memory. By default, 1 GB is reserved for this space, but it can be configured using the JVM option compressed class space size. An important point to note here is that the JVM option max metaspace size sets an upper limit for the committed size of whole of the metaspace, including the compressed class space. Apart from the Java heap and the metaspace that are managed by the JVM, a Java process allocates in native memory too, which is not managed by the JVM. Out of this native memory, thread stacks, loaded jar, zip files, native libraries, and native resources are allocated. Allocations done from the native code, JNI or JVMTI code are also made from native memory. Native memory is limited by the 4 GB process size limitation on 32-bit machines and the available physical memory on the 64-bit platforms. Here are some examples of running out of native memory. In the first example, JVM's internal code chunk pool tried to allocate in native memory but failed due to lack of space. In the second example, JVM's attempt to create a new thread failed because there was no room left in native memory. This error message means that the JVM is not able to allocate from native memory, and this failing process or other processes on the system are consuming all of native memory. This error message could be an indication of a native memory leak. To summarize, here's what we have learned in this lesson. Misconfiguration of memory pools, memory leaks, excessive use of finalizers, and explicit GC invocations are some of the primary causes of memory problems in Java applications. These causes can lead to long GC pauses or excessive GCs in Java applications, which can then manifest as performance problems, unexpected memory growth, and application failure with out-of-memory errors. And that brings us to the end of the lecture videos for Lesson 2. Your next step is to try Lab 2, where you'll first run a test program that fails with an out-of-memory error exception, and then another test program that shows abnormal memory growth in the metaspace pool. You will monitor these processes using the JConsole and Java Mission Control tools. Once that's done, you should be ready to try quiz number 2. Thank you.